Hello everyone and welcome back to another episode at the Hidden Quantum Champions. My name is Jonas and in today's video we are going to look at a company from Oxford. With that, let's dive right into it. So here we are on the website of Oxford Ionics, delivering the world's most powerful quantum computers. And then here we see a basically, cryostat sample holder. So what goes down to very low temperatures with some computer chip looking thing on it. And we also see some magnifying glass here. We are combining our high performance trapped ion platform with semiconductor supply chains for scalable market ready quantum systems. So there's also some information here on the technology, but I guess we will learn more about that in a second. So quantum computers are the most powerful form of computer that the laws of nature allow. So that's referring to the fact that if quantum theory is the correct explanation or the correct description of the universe, and up to now it is our most accurate theory by far. So when we look at measurements and we compare them to what quantum theory predicts, we see that it is like from an accuracy point of view, the most accurate theory, so the most accurate description of the universe. If this is true, then actually utilizing that, like utilizing quantum mechanics to perform calculations is something that should be very precise, because in order to simulate nature, we are using nature the way that it is. So basically that's why quantum computing is, let's say, the ultimate or most powerful form of computers. Hence the statement here, right? Quantum computing will improve productivity, sustainability, and quality of life by transforming our ability to tackle real-world problems across fields including chemistry, logistics, and finance. These are the favorite ones that we always hear about. So quantum computers in chemistry, in logistics, and in finance. Only one technology platform has achieved the performance needed to unlock this massive potential: trapped ions. But ions have been hard to scale until now. Oxford Ionics' unique approach combines the world-leading performance of trapped ion qubits with the scalability of semiconductor manufacturing. And that's basically the statement. And there are some news here on the website, and we will go on the news section later on because I think there's some interesting and important thing as well to mention there. And with that, I think we've seen the first page. Maybe let's quickly check out our technology part, which leads us right away to the tech section. So now we're looking at how the combination of silicon technology and the ion traps actually works in practice. So launching a new age of computing. We see here, I guess these points, they are the traps. We see here light sources, so probably some like LED type of things that are integrated in here that are manipulating. Then this could be, I don't know, some readout electronics, or maybe also manipulation of the ions themselves. What else do we have? Well, I mean, we will learn about it when we scroll down here. Something that I can already say, like looking at the website, it's pretty cool in terms of design. You have these fancy animations here. Then you have this like very nice and technically interesting looking photo of the system. Of course, there's like Kapton tape and wires around here. Then we see like a PCB. So I think it looks like from an optical point of view, very, very interesting. It says the future is quantum. Quantum computers are the most powerful form of computers that the law of nature allows. Okay, that we've already seen. Trapped ions. Okay, our qubits are individual atoms, the universe's closest approximation of a perfect quantum system. We remove one of their electrons to make them ions, allowing us to hold them less than the width of a human hair above our ion trap chips. So basically, that's maybe also important. Like we've seen other types of qubits before, like for example, superconducting qubits. And this is in a way an artificial system which reassembles a qubit. So you create a quantum state, like for example, in a superconductor, you have this bosonic state. So like a a state that can, even though it involves multiple electrons or bosons, like Cooper pairs in this case, even though multiple of these are in there, you can essentially treat it like a single quantum system. However, the problem with that is that actually, because you create it out of these like smaller sub elements, these qubits, they are never exactly the same. Like, for example, if you have, I don't know, a specific wafer and there's impurities in there, they might influence your qubit. So when you start operating them, that means you basically have to kind of measure every single qubit first, understand first how they actually behave, and then tweak and tune your signals a little bit such that they actually control the qubit in a nice way. This is not true if you use atoms or if you use ions in this case, because every single atom that is like, I don't know, a copper atom or rubidium atom, they always behave the same way. Like a helium atom is always a helium atom. Okay, there might be cases where you have like additional isotopes in there, you can clean this out, but like, let's say every standard helium atom behaves the same way. And now this is important because when you then do this computation with ion traps, that basically means you don't have to tune your qubits. Every single qubit or every single ion behaves exactly the same way. You can use the same type of laser pulses, and you don't have to do this fine-tuning before you start actually operating. And that's why it says here the universe is a closest approximation to a perfect quantum system. And okay, then they use this silicon technology, so they probably have like electrical gates that then behave like an ion trap, so that they can trap these single atoms right above the chip. So you create a vacuum environment where there's no air, nothing in there, right? Then you basically have those ions. So you first need to ionize atoms. So you remove one electron, as also mentioned here, so that they become electrically charged. This way you can actually electrically control them because now they have a charge. So if you apply a magnetic field, you can drag them around. Of course, there's a lot of stuff happening in between, right? You have to cool them down, make sure that they are operating at a cryogenic level so that they don't have too much thermal power in them and shake around. So there's a lot of other stuff happening. It's a complex thing, but that's like the simple description of it, right? Until now, let's jump back to the website. Until now, trapped ion computers have largely relied on lasers to control the qubits. This approach performs well for small processors, but becomes untenable and error-prone as the size of the processor scales and the number of qubit increases. And that's also something, if you look at like a typical ion trap setup, the ion trap itself is a pretty small and confined space, right? You have like this super tiny chip where actually the ion trap is placed. Usually that's like in a vacuum tube with a window in it. But then you have this whole setup of lasers around it, and the lasers, so you need multiple lasers. But then actually with these lasers, you also need some mirrors attached because you can't like put every single laser right in front of the window. So you have mirrors that are bending the laser beams around, and then you might have lenses in there as well to change the beam, beam shape. So there's a lot of stuff going on, and at the end, you have this super small ion trap, but then you have a full table full of optical components. And here the promise is, okay, you put the light sources, so the lasers, on the same chip, and that way I guess you make it smaller, and also because you don't have all of these mirrors and things which can kind of derail your operation. Like if the mirror is slightly little bit tilted, it might not end up at a spot where it's supposed to be. But if you have, let's say, the laser source right below the actual ion trap, like a couple of micrometers below, or maybe even nanometers, okay, then it might be easier to line those things, right? So this approach performs well for, that we already had. Instead of lasers, Oxford Ionics trapped ion processors use a proprietary patent electronic qubit control (EQC) system for control of the qubit. This allows to combine the univariate quantum performance of individual atoms with the scalability and reliability of the electronics integrated into silicon chips. So, okay. step back. Here we don't use, let's say, classical light sources like lasers, but actually there's this EQC, which is doing the control of the qubits, so electrically, right? Our approach to quantum, better beats bigger, is a quantum computer with 1 million qubits better than one with 100 qubits. It depends on how good the qubits are and how they're wired up, the error rate and the connectivity. A quantum processor chip with just a few hundred perfect qubits can solve problems beyond the reach of any supercomputer, but if the qubits aren't good enough, the same problem can take a machine the size of a warehouse. Everything we do at Oxford Ionics is about building better, not just bigger quantum computers. That's why we are build our devices with complete connectivity between qubits, and we use the technology which has the lowest error rates ever demonstrated. Controlling our qubits using electronics integrated into silicon chips allows us to do this with the processors built in the same factories that make chips for cars and phones. So again, like silicon technology, which we already know, which is pretty well developed, like billions of dollars, euros, whatever currency you want in investment that have already happened in this to build the chips that we have today. And basically the technology that they are using is building on top of that, like silicon standard technology. And then, yeah, that's also an important point here. So there's a philosophy question, and that's actually something which is currently debated. So there's the question, do you need more qubits or less qubits? And right now we are in this NISQ area where like we don't have perfectly operating qubits. So we cannot really utilize the full power of the promises that we have in these quantum algorithms, because the machines are making errors, and these errors, they're problematic for the calculations, and actually it is not so easy to mitigate them. So now there are like two different thought schools or ideas here. Like one is to basically push the accuracy of the qubits further and further so that they make less errors, and thereby you can, with a small number of qubits, already start to do the first let's say reasonable and application-oriented things with it, even if you don't have, let's say, any sophisticated error correction algorithm on top. The other side to it is, if we had some error correction schemes, we might not need perfectly well-functioning qubits, but we can actually work with ones that are not working that well, and then we just put our error correction code on top, which helps then to correct these errors in the system, and thereby you kind of simulate perfect qubits by just taking more than a single qubit, but like a lot of qubits, and chaining them together with this error correction algorithm. And there's like first examples of error correction algorithms that have already been implemented and published, like different, let's say, research groups that have been operating system with a quantum error correction code on them. So there are like these two different ideas. And in this case, like for Oxford Ionics, we are on the side where like we want to optimize the accuracy of, let's say, rather a small but high quality set of qubits, rather than like a big one that uses error correction right away. And I mean, that doesn't say that like they don't want to use error correction, right? It just says that they want to have a precise qubit starting from it. Okay. Here it says a couple of things about the company. Oxford Ionics is built on decades of leadership at Oxford University, home to some of the first pioneers of quantum computing and birthplace of quantum error correction. So error correction we talked about before. We define the frontiers of what's possible with our team setting numerous world records, and including the best quantum gates, longest quantum memory, coherence times, and the best quantum networks demonstrated anywhere in the world in any technology. We accomplish things no one else can by bringing together the best physicists and engineers to build a completely new kind of technology. Very good. There's something here about the team. So here we can see a couple of people that are like, so we have the CEO and the CTO. That's a very, let's say, sympathetic view that you can see, like the faces behind the company. You have the CFO, VP engineering here, They're like the different teams: science, engineering, infrastructure, and operations teams. And you can actually see some people that are working here in the team. And of course, there's like the Join Us button here, which leads us to the careers and open positions. Then we also have a news and events, a blog, and a careers page here. And then, of course, the contact one. Let's quickly check out the news and events. So here we see Oxford Ionics delivers quantum computer to the NQCC. Okay. Then we can quickly check what else do we have here. So there's like news coverage here. We have the LinkedIn feed here, where to find us. So these are like the events that they are participating. So by the way, also interesting, like if you are interested in the world of quantum, I can really recommend you to check out these companies' pages, because usually there's like an interesting collection of events that are happening within the year somewhere on their websites, and you can actually find where they will be actually exhibiting, and thereby also maybe find events that could be interesting for you. Let's quickly look at all announcements, because there's one which I wanted to hop on in particular, which is this one. IonQ announces agreement to acquire Oxford Ionics. So I think IonQ is maybe an interesting company to know about. They're like probably from a capital point of view the largest stock listed company right now in the space of quantum technology or quantum computing. So they are building ion-based quantum computers, and they actually they announced that they will acquire Oxford Ionics, which I think is a very interesting move, because now we see that like there's at least some consolidation happening in the market. So you really see there's like leading labs or leading companies starting to form in the different types of technology. Like, for example, in the annealing market, you have D-Wave as a very big label. Now we have IonQ as basically like a leading label in the ion-based quantum computing space. And I'm really excited to see what will be the next ones where we see these types of activities happening. With that, I would like to close today's session. As always, make sure to stay hydrated, and see you in the next one. Bye-bye.